Okay. So thanks for the invitation, and I'm excited to be here, to come back after a while away. So what I'll talk about today is a joint work with a great graduate student at Columbia from the IOR department, Jalaj Bandari. Okay. And this is I'll tell you about some attempt to understand the convergence properties of a really widely used method in reinforcement learning called policy gradient methods. Okay. And just to give some context, I work often on reinforcement learning, but mostly on the exploration problem. So sort of on how you can learn in a statistically efficient way by collecting the right data. Okay. Now this is sort of a twist where mostly we're going to be thinking about things more from an optimization perspective, understanding the landscape of certain loss functions and so on. Okay. Now, I think the approach we take is going to be colored sort of by sitting between machine learning and operations. Okay, so we're going to be studying this class of heuristic methods, I guess, that are widely used in reinforcement learning. But I myself regularly teach like PhD courses on dynamic programming. Okay, so I'm going to try to understand these methods through that lens in an appropriate way. Okay. So here we go. Here's sort of the outline. I'm going to spend a while telling you what policy gradient methods are, give you a flash of the exciting things people are doing with them, and explain kind of why it's not clear, despite the fancy things people are doing, whether these ought to solve even really simple problems that we know how to solve in other ways. Okay. And then I'm going to kind of go through a warm-up where I explain a really simple task on which policy gradient methods will essentially fail to converge. They're going to get stuck in a really bad local minimum, even in one of the simplest two-state problems you could even think of. And from there, we're going to kind of go through the main insight of the paper, which is understanding structural conditions that are shared by many classical control problems under which these policy gradient methods are going to actually succeed. Okay. And that's really the punchline of the talk. If there's time at the end, I'll talk about kind of approximation results where you use large policy classes. I'll talk about convergence rates and things like that. Okay. So here we go. What are policy gradient methods? Well, in the simplest way, there's sort of a few lines of pseudocode that you can read about on a blog post or something. And then implementing those appropriately, along with an enormous amount of engineering, leads to some pretty cool things. Okay, so it's being used in robotics, in game playing, and so on. Here's a demo of a pretty cool result recently from OpenAI. They're solving a Rubik's Cube just with tactile sensing on the different digits. All right. This is a kind of task that I think was out of reach until very, very recently. And getting things like this to work via any method is pretty impressive. Okay, so this is a high-dimensional, kind of from a control perspective, it's a high-dimensional continuous control. It's high-dimensional because the state is sort of involves kind of all these different sensor measurements that you're collecting. Okay. And now, what these methods are doing is essentially mapping this high-dimensional state directly into an action that you take at that state, sort of a force to exert on the different motors. And it's sort of captured well by this, this picture here. Okay, we're going to go from raw pixels in this video game, and somehow we're going to have to do computer vision to understand what's going on in this game, but we don't do that. Right? Instead, we build a neural network that directly maps the board game into an action, which here is the probability with which you move the Pong paddle up instead of down. Okay. All right, so the first sort of thing that one should be maybe interested in here is that this is a completely end-to-end approach. You're directly maximizing the thing you might do inference on. You're directly mapping that to actions. And you're searching not over kind of just trying to find the best model and then to optimize that model or so on. You're directly maximizing the thing you care about over the parameters of this neural net. Okay. So let me contrast this for a second with another common approach in reinforcement learning, value function approximation. Okay, so here's kind of an old example used to motivate value function approximation. It's the problem of playing Tetris. Now, one approach is to approximate the value to go in this problem, so the expected number of rows cleared, discounted out into the future, by a linear function of the features of the board state. Okay, and the kinds of features people have used before that seem to work are things like the heights of each of the columns, as well as the, you want to capture something about the height of the highest column, so the maximum of the heights. And you want to capture that jagged boards are bad for playing Tetris, so you use inter-column heights. Okay. You put all those down into a feature vector. This gives you a value function approximation. Okay. Now, how do you go from that to a control? Well, the usual idea is actually I understand very well for the different places I could put down a block what the next state of the board will be. I kind of know the dynamics. So we select actions by taking the best position we could put this down, estimated by the next state of the board you'll be at. Okay. So people have done this going back maybe almost 2 decades. People did this for Tetris. It turns out something that actually works even better is instead of doing that argmax greedily, we're going to write down a parameterized class of policies where the probability that I play a given placement of the block is proportional to the inner product, e to the inner product of the feature vector associated with that state and some weight vector theta. Okay. Now what I do is I just search over vectors theta to find the one that optimizes value to go. Okay. So I'm just solving sequential decision-making problems by search. Okay. And it's interesting, if maybe a bit disappointing, that just direct policy search like that is working better. Okay. So let me cast all this in a slightly more formal lingo. Here's what we're doing. We have a cost to go function. So I'll be doing minimizing cost instead of maximizing value, which captures the expected cumulative cost incurred, discounted by a factor gamma, from any initial state S. Okay. Now that's under some policy pi, which, okay. Now, in usual dynamic programming, you try to maximize or minimize this cost to go from every single initial state. Okay, so usual dynamic programming is a multi-objective problem that you're able to solve. Okay. But when it comes to doing, say, like gradient descent, we need a scalar loss. And policy gradient methods are usually defined by thinking through the average cost to go under a random initial state that's drawn from some distribution rho. Now, often, if you look this up, they won't highlight this. But for all of our results, it's going to be essential that this rho is supported on the entire state space. Okay. So I'll show you one simple example where these methods don't work if you only care about training with a rho that's, say, degenerate. Okay. All right. Now, what we do is we want to minimize that cost to go L over policies. But there's too many policies in this problem. Okay, so what we're going to do is impose some kind of knowledge that maybe a certain class of policies should be good. So we write down a parameterized class here, pi theta. Okay, so pi capital theta denotes a subclass of policies that depend on some parameter theta, like the ones you saw before. And that's a subclass of what I'll denote by capital pi, the set of all stationary policies. Okay, a policy here is a mapping from states to actions, determining how you play in any given state of the world. All right. Now what we do is just do SGD on this loss function. Okay. So we say the new parameter should be the old one minus a stochastic gradient, all right, times the step size. What's sort of nice is even though that function L is usually not available analytically, it's pretty easy to compute unbiased stochastic gradients. Okay. So there's many variants of methods that compute those, that can give you these kind of gradient estimates. The simplest one is the so-called reinforce algorithm. Now, what I do for a discounted problem is I'm going to do a rollout by applying the current policy for some number of steps. The number is randomly drawn and depends on the horizon. Okay. Now, I sample an initial state from my initial distribution rho. I generate that rollout from there. And then there's just this very simple function, which it turns out is a stochastic gradient of the loss function L. Okay. So this is the kind of thing that any of you could probably get working in one day, coding it up even from scratch. Okay. Now, there's many variants and improvements to this sort of thing. In some of the examples we've run, we deal with like inventory control problems where the dynamics are smooth, in which case there's better ways to get gradients. All right. I'm not going to be focusing really on how you compute these gradients, and I'm instead going to be studying the properties of the loss function L. Okay. Here's sort of the bummer. We have these methods that seem like they're solving some very hard tasks. And it seems like we've done something nice where we've replaced maybe a field we haven't studied that much, dynamic programming, with something we've studied very deeply, gradient descent. And now we're going to use gradient descent to solve dynamic programs. The issue is, it's not a very satisfying reduction, because we reduced a class of problems we knew how to solve to black box non-convex optimization. Okay. Because that loss function L is almost always non-convex. Okay. Now, that's going to be true even for the kinds of problems that we know how to solve via other methods. Okay. So as a result, if you open up a textbook in this field, it says that what's good about policy gradient methods is, unlike some other RL methods, you know that they're stable. They're going to at least converge to a stationary point or local minimum. Okay. So something like you will eventually converge to a point where the gradient is 0. Okay. But there's almost no guarantees available on the quality of stationary points of this objective. And what I'll show you in a moment is there are bad local minima in extremely simple problems. Okay. So that is really the challenge that I want to understand in this work, is does it make sense to be running gradient descent on this non-convex function? When does this work? And if so, why? Okay. I want to highlight that there's a limited scope, therefore, to what we're doing. Okay. There's actually many issues with policy gradient methods, despite their promise. And we're focused really on this first one. You're running gradient descent on a loss function that's non-convex. And so should that work? Okay. Now, some other ones we're sort of sidestepping. One, there's a whole business of running natural gradient methods in these problems, dealing with the issue that you really only care about the policy you select. Okay, and it could be that certain parameters, the distance in parameter space is not well aligned with distance in policy space. And so people have kind of essentially change of coordinates, second order methods that deal with that. Okay. Now, there's another issue, which is that the variance of these stochastic gradients could be large. Okay, so it might be sample inefficient. I'm really imagining in these problems that you have a simulator, like many of these systems do. And so maybe the most fundamental question is, if you ran this thing for long enough, would it eventually work? Now, the last issue is not always appreciated, is exploration is an issue. Okay, so it's sometimes said that if you use a stochastic policy, meaning there's some randomness in how you choose actions, then that's going to ensure that you explore and make sure that you can estimate the gradients of that function L. Okay. Now, there are these really simple examples that were known a long time ago that show that basically it would take you an exponential in the number of states, many steps, to solve such very simple problems if you do not have a restart distribution row that navigates the state space for you. So this way, where every once in a while I randomly start the problem at an initial state and compute my stochastic gradient starting from there, that's sort of critical. Okay. All right. So conceptually, you should think of what we're doing here as being related to a line of work that for a bunch of specific machine learning problems is looking at the landscape of the non-convex loss function and trying to understand, okay, if we have methods that reach local minima of this non-convex loss, are those local minima any good? Okay, and if so, why? All right. And I'm trying to sort of do that for policy gradient methods. All right. So let's start with the bad news, which is that non-convexity is a real issue, and it's a real issue in the simplest settings. Okay, so here's my bad example for policy gradient methods. And weirdly enough, I don't think this sort of thing has appeared in the literature before. Okay, so I have a two-state MDP. There's a state left and a state right. Okay. From state left, you can either stay left and incur a cost of 1 per period. G here is the cost. Or you can go right. Moving between states incurs a cost of 2. Okay. But from the right state, you can stay right and earn a cost of only 0.
So transitions are deterministic.
Transitions are deterministic, but moving is costly. Now, if you have a long discount, if you have a reasonable time horizon, so I think if your discount is bigger than 1/2 is the threshold, then the optimal policy is from either state to move to the right and then stay right all periods thereafter. Okay. Very simple problem. Okay, now behavior like that is captured by a parameterized policy that has only one parameter. Okay, so there's going to be a number, theta, that's between 0 and 1, and that's the probability that I move to the right regardless of the state I'm in. Okay? So theta equals 1 is the global minimum of this. Make sense? All right. Now here I'm plotting the loss function as a function of theta, and you can see it's not convex, it's concave. And so there's two local minima, one at the left corner, one at the right. The global minimum is the one on the right. And if you started with a fairly low level of theta, you're going to get stuck on the left. Okay. Now, what's sort of the intuition here? If I have a small setting of theta, what that's saying is that I almost always go left. Okay. Now, suppose I deviated and then went right. okay, although going right would align with the optimal policy, it hurts me in this case. Because once I move to the right state, I'm almost immediately going to move left again. And that's no good, right? The worst thing you could possibly do in this decision problem is move right, then left. All right. So somehow, my policy class is rich enough to contain the global minimum. It's very simple. It's a one-dimensional kind of convex family. But the non-convexity of the loss means that I can get stuck. All right. And so the way to internalize this is, despite containing the optimal policy, the family is not rich enough to contain descent directions away from this local minimum. Yeah.
Parameterization is important, right? Firstly, you use a single parameter for both states.
Great.
And secondly, you're just using theta. I would have done theta comma 1 minus theta vector. Now it's a 4-dimensional manifold, and then I don't know if it's convex or non-convex.
Great. So it's not going to be convex. No matter what, it's not going to be convex. But there is a way to cure this bad example. All right. So let me tell you. I'm going to cure it, and then I'm going to say why the story seems a little disappointing. Okay. First, this is a little disappointing because it says that, hey, we're running these very complex methods. It's a little disconcerting when they fail in what seems to be the nicest possible setup. Okay. Now here I'm going to fix it through what you said. Let's add 2 parameters. Okay. So now there's a parameter that controls the actions I take from the left state, a parameter that controls the actions I take from the right state. That's now the class of all possible policies in this problem. Turns out that as a function of these theta L and theta R, the loss function is still non-convex and is somewhat wild. Okay. But policy gradient methods do converge to the global optimum. Right. What you do, say, starting from something like theta is 0.3, 0.3, you immediately move in a way that looks like it's mostly misaligned with moving to the global optimum. Okay. So at first, you sometimes move right from either state. And you immediately correct so that you move right from the second state. Okay. But from the left state, you stay left. Yeah, question?
What do the axes mean?
Great. So the horizontal axis here is the theta L parameter. Right. So the theta L parameter is, thank you for the question. Should have said that. The theta L parameter is shooting up to 0 immediately. Theta R is gradually increasing. Once I reach a point where I mostly stay right if I go right, then I start to correct theta L to the right direction. Right. So this is a weird trajectory that kind of reflects doing gradient descent on a non-convex loss. Hint, hint, it's kind of going to reflect what policy iteration does.
But now you're not economizing anymore, right? The dimension is as large as the dimension of the original policy space.
Yeah, I think that's exactly right. So the disappointing thing here is that somehow in the motivation for policy gradient methods, you say that you need some inductive bias on this problem in order to get things to work. Right? If the state space is enormous and intractably large, something must be simple to learn an effective controller. And I might believe that, hey, the policy class is simple. Okay, so if I have a good prior knowledge about what policies ought to look like, then I can just search over that. We just saw that searching over the class of policies, even when it's simple and contains the truth, may fail. Here, you resolved the problem, but it required seemingly using all possible policies. So already there's some hope and mystery. It fails in one case, succeeds with a richer policy class. But if it succeeds only with all possible policies, something's disappointing. Okay. So there's some reason for hope. Okay, now really this paper, the paper I'm presenting today, is prompted by having read this one by Fezel et al., which show that in a deterministic linear quadratic control problem, policy gradient methods reach the global minimum. Okay. Now there, the natural class of policies to consider is the class of linear policies that take the state, which is a vector, and multiply it by a fixed matrix to determine its control. That class is known to contain the optimal policy, and so they search over it using gradient descent on that matrix. Okay. Now, that problem is non-convex. It's not quasi-convex. It's nothing nice. And yet, they reach the global minimum. Okay. And the proof involves kind of intricate analysis of the various matrices that show up in linear quadratic control. Okay. So I'm sort of wondering what was special about linear quadratic control that does not hold in this example in the top. Now, adding to the mystery, kind of in a separate line of work, there's an inventory control paper which shows that gradient descent on the class of base stock policies in a finite horizon inventory control problem converges to the global minimum despite non-convexity. That proof also involves kind of intricate analysis, and one that, to my understanding, is very different from that of Fezel et al. Okay, so why does this work sometimes? Why does it not work other times? And can we have some simple understanding of this? Yes?
By enforcing the first policy class, you seem to be actually solving a partial observant between also.
It's not partially observed. I'm not sure why you.
By enforcing a single parameter, you don't know what the state is. Can't differentiate between the two states.
No. So I'm not changing the problem, but I'm changing the policy class. I think you're right that I'm not allowing the policy to take different actions at certain states.
Sometimes say that's equivalent.
So I wouldn't say it's equivalent to a POM-DP because I still, I'm not changing the problem, and I'm not changing the data I collect, but I am changing the flexibility of my controller. Okay, and I think that's important somehow that if you have a problem with 10 to the 10 to the 10 states, you can't allow your policy to take completely independent things at different states. Somehow you need to generalize across states. And that's sort of what we're all doing when we run these policy gradient methods. The question is there any hope for that to work? Okay. So here's going to be the kind of main insight following off of this stuff. Is we're kind of going to unify the mystery before. So we're going to have general conditions ensuring that this loss function L has no suboptimal stationary points, okay, despite being non-convex. Right, so just kind of a refresher, for unconstrained optimization, a stationary point is a point where the gradient is 0. Okay, so if you run a gradient descent method, you kind of make progress until you get stuck where the gradient is 0. For constrained convex optimization, a stationary point is a point satisfying the first order necessary conditions of optimality. It's a minimum of that constrained problem if you linearize by the gradient. And generally, constrained first order methods like projected gradient descent reach a stationary point in that sense. So if we reach such a stationary point, is that any good? Under these conditions, it is good. All right, so these conditions apply to kind of the problem I just showed, where you have the class of all possible stochastic policies. It applies to linear policies in linear quadratic control, to a certain class of randomized threshold policies in optimal stopping, and to base stock policies in finite horizon inventory control. As you would expect for this to be a theorem, it does not apply to this problem, which had bad local minima. Okay. And so it's sort of, these conditions seem to divide the class of problems for which these methods work, up to what we know, and the class where they don't work.
So do these problems have any bad stationary points?
They do. So this is one. So this corner at 0 is a bad stationary point.
No, but that's with that parameterization. I'm talking about the problems on which it works.
No. So the problems on which it works have no bad stationary points. Yeah, so that's sort of what we're proving, is trying to understand why is it that for some problems there are bad stationary points. For other problems, despite being non-convex, this loss has no bad stationary points. Yes?
So does this in the end incurs condition on the underlying Markov chain? For example, that counterexample is like periodic. So for example, you require your Markov chain is irreducible or non-periodic or something. Or is it more general?
Good. It's sort of more general than that. Interestingly, it's going to be more have to do with well, I guess you'll see.
So one more
So-
quick question.
yeah.
Loss function depends on the row.
Yes.
Does this property of bad stationary points, does that depend on the row?
Great. If there's time at the end, you'll see the row dependence coming up more explicitly. It does. So it's sort of there being no bad stationary points is when row is supported everywhere in these problems. So sort of the row needs to explore the state space.
Oh, that's all.
That's all. Yeah.
I mean, when I look at this, it looks like it's like sort of a local convexity condition around a solution or the solution, right? But you're saying just that local condition means there's no stationary points anywhere?
Great. So it's actually not going to be. Oh, I see. So this is actually what I'm saying on the right is this is the definition of a stationary point. So this is saying a point where you can't make local progress. And what I'm saying is under certain conditions that I'm going to have to show you. Under certain conditions, if you're stuck at a stationary point, you're stuck at the global minimum. Right. And so why? Okay. Seems I've teased the mystery well. You have to bear with me for 2 slides. So I have 2 interludes, and then we're there. Okay. So interlude 1, reinforcement learning is a field where 1,000 papers get posted per month. And so when you do something like this, there's always related work that comes out at the same time. So 2 papers came out around the same time. One by Alec Agrawal et al. And by Liu et al. They're both understanding essentially variance of natural policy gradient with very large flexible policy classes with a focus on trying to understand rates of convergence. All right. Now, while we have some rates of convergence that I'll show you at the end, that's not really our main focus. I think that kind of the dividing line between these sets of works is that the general conditions that I'm going to show you that apply beyond kind of finite state, finite action problems and apply to things like linear quadratic control, those are independent in our work. Okay. Now, interlude 2, to kind of even make sense of the conditions I'm about to tell you, you need kind of to remind yourself what the policy iteration algorithm is. Okay. So not so surprising that what we're going to come up with goes via route of policy iteration. In some ways, that's like the well-understood cousin of policy gradient methods. Okay. So if a non-convex problem has nice structure, there should be some kind of hidden easier problem or hidden nice structure in it. Here, the hidden nice structure is going to come from thinking about policy iteration, which solves these sequential decision-making problems by solving a sequence of much easier single-period problems. Okay, and in some sense, that's the nice structure that's present in dynamic programming problems. It's this temporal decomposition. All right. So what is policy iteration? Okay. Given a policy pi k, I update it in the following way. I think, okay, instead of doing what policy gradient methods do, which they think, what's the best policy to apply throughout the entire horizon? They say, assume I'm going to apply pi k from period 2 onward. Okay. Now, given the policy I'm using from period 2 onward, I'm going to solve a one-period decision problem, which takes the best action from any initial state S, which minimizes sort of the immediate cost incurred plus the cost to go under my base policy. Okay. Now, I do something a little incoherent. Even though I've solved this one-period problem, I take the result I got out, and I use that as my new policy for all periods. Okay, and I repeat. All right. Now, when in RL, you usually call this thing the Q function. Q pi of SA is the improvement upon, or sorry, measures the cost to go if you take action A from state S and apply pi thereafter. Now, just like we went from the cost to go, question? No. Just like we went from the cost to go j to a scalar version L, I'm going to go from this cost to go q to a scalar version. Okay, so let's introduce a state weighting eta. And for a new policy pi plus, define this kind of weighted cost to go where I average over states drawn from eta. Okay. Now, the policy iteration update gets the argmin for every single initial state, S. Okay? And so the policy iteration update also minimizes this thing, C. Okay. All right. And it's more or less you have uniqueness as long as eta is supported everywhere. Any questions on this?
Just understand your notation. Is pi plus the decision rule for choosing A?
It is.
Okay.
Pi plus is like, think of pi plus as like pi k plus 1 and pi as pi k.
Okay.
Did that help? What's eta? Eta is a distribution over the states. So I'm going to define this. It's eventually going to be, eventually the results depend on a particular choice of eta. But it's any, so this is a function of three things. One of them is the state weighting. Yeah. Okay. So this is a way basically of scalarizing a multi-objective problem. All right. Now, a big comment is that C and Q, these kind of things that involve a one-period decision problem, are much, much simpler than the loss function that policy gradient treats. Okay. And you'll see that kind of more explicitly in an example in a moment. Okay. So just as my comment, in the kind of natural case where what I'm picking is a probability vector over k basic actions, the Q function is just a sum of the Q values weighted by their probabilities. Okay. So as a function of the probabilities I play, this one-period problem is a linear optimization problem. Okay. Clearly quite nice, clearly convex, all these things. All right. So in some sense, what you can see these conditions that I'm about to show you as being a reduction from having to think about this nasty non-convex loss that results from the multi-period problem to thinking entirely about the structure of that policy iteration problem. So I'm going to give you two conditions that ensure this loss function has no suboptimal stationary points. The first is that the policy class is closed under policy improvement. Here I use policy improvement synonymously with policy iteration. Okay, what does closure mean? It means that if you start with a policy that's in the policy class, so you have a threshold policy in optimal stopping. Now you try to do a policy iteration update to that, yielding a new policy. Okay. In general, there's no guarantee that that new policy would be a threshold policy itself. But it turns out that for optimal stopping, that is true. The policy update starts from the policy class, stays in the policy class. Okay. Makes sense? So written out this way, I sort of have this one period optimization problem. Policy iteration solves that over all possible policies. Our condition is that you could solve that just as well by solving that one period problem within the policy class. All right. So I think this is really the key condition in the work, and the second one is maybe secondary. Okay. So what is this? This is a sense in which the policy class is sufficient for the control objective. Okay. Now, necessarily, it's stronger than requiring that the policy class contains an optimal policy. Okay. Because I showed you an example at the very start where the policy class contains the optimum, and yet you can't find it efficiently. Okay. But it's much, much weaker than saying that the policy class represents nearly all policies. Okay. Instead, what I hope is that the policy class is aligned enough with the objective that I can solve certain decision problems within it. Okay. Now, what we'll come back to at the end, if there's time, is sort of adding an epsilon here and seeing whether all stationary points are nearly optimal. Questions here on sort of what this means? All right. Now, the second condition, well, we're doing a local search. Okay, we're not exactly solving the policy iteration problem. And so this doesn't make any sense unless there's some local structure to the problem that makes it amenable to doing so. Okay. So the kind of a smoothness that we need is in the single period problem. We need basically that you could solve the policy iteration problem by a first order method. Okay. Does that make sense? And remember, the policy iteration problem is often linear, in which case this is immediate. Okay. So let's go through this concretely for one of our motivating examples, which is linear quadratic control. Okay. Just for simplicity, I'm going to treat in this talk the deterministic version of linear quadratic control, so there's no noise in the dynamics. What's this? This is a problem where states evolve according to linear dynamics. So I take this previous state, I multiply it by a matrix, and I exert some control, at minus 1, and multiply that by a matrix to get the new state. Okay. Now what I'm interested in is choosing these controls to minimize the discounted sum of these single period convex quadratic losses. All right. Now it's known that the optimal policies in this case are in the class of linear policies. Okay, so there should be some theta, theta star, out there, where the optimal policy just takes the current state and multiplies it by theta star. All right. So a natural thing is to try to just search over the theta parameters using kind of gradient descent. Now, trying to get a handle on things directly is a mess, because the total loss that you incur as a function of theta is messy. Okay, the total loss is the discounted sum of the single period losses I'll make at state st. And now really where the non-convexity is coming from is that the state at time t comes from applying these kind of linear dynamics repeatedly. Okay. And that's reflecting that my controller changes the states kind of in this recursive fashion. Makes sense. Okay. So past work kind of gets a handle on, hey, there's some quadratic cost function that is induced by my controller. And I'm going to search over the thetas that make this quadratic small. And manipulating these expressions gets to be pretty crazy. So let's go this side route where we just check the two conditions. All right. So by contrast, policy iteration is pretty simple in LQR. The single period problem that policy iteration solves is a quadratic optimization problem. Okay. I minimize the sum of the instantaneous costs and the cost to go, both of which are quadratic functions in A, the action I choose. All right. Okay, so our first question is, if I start with some linear policy and I apply a policy iteration update, do I get a linear policy back? Okay, and that answer has been known at least since 1968 and is pretty easy. Okay, so you can sort of just eyeball that if you minimize this quadratic, you get out some function that's linear in the states. Okay, and so I start with a linear policy, I end up with a linear policy. That's kind of the magic of linear quadratic control. Okay. Now the next condition is that the policy iteration objective has no suboptimal stationary points. Right? That you could, in principle, solve the policy iteration problem via gradient descent. Now this is a quadratic optimization problem. So yes. Okay. It's convex. All right. So we're done. We've sort of verified that policy gradient will work on linear quadratic control. And it doesn't really require any math. It just kind of requires citing textbooks. All right. Does the idea make sense? All right. So I guess what I've sort of omitted is why those conditions? Why did these conditions make this work? Okay, so not for all the problems, but at least for linear quadratic control, there's a pretty intuitive proof. Okay, the intuitive proof is, say, if I start with a stable linear policy and it's not optimal, then what we know from policy iteration theory is that the policy iteration update gives you a different policy. Okay, so now I have two policies, one theta that I started with, and an updated one, theta plus, that's better. Okay. Now I want to show that the loss function has no suboptimal stationary points. Okay. In order to do that, all I have to do is exhibit a particular descent direction, a direction of local improvement. So the natural candidate is to move in the direction of the policy iteration update. And once you get this idea, a short kind of like a one-paragraph dynamic programming argument shows you that you do reduce cost by moving in the direction of the policy iteration update. And the extent to which you reduce it depends on the gap in Bellman's equation, sort of how far the policy is from optimality as measured by that gap. And to your question before, the rho kind of shows up in measuring this norm. Okay. So what did we use when we did this proof? Okay, one thing we used is that the policy iteration update is in the policy class. Otherwise, that's not a descent direction you can move. Okay. The other thing you're using is some kind of convexity structure in the one period problem that means that moving in that direction gives you local improvement and it's not just improvement at the end. Okay. All right. So I'll just sort of hint that the key observation in a more general proof is a bit different. And it involves kind of relating the gradients of the policy iteration objective to the gradients of the global loss. Okay, and it's sort of like a reinterpretation of what policy gradient theorems tell you, for people who know what that is. Okay. All right. So just the last kind of bit of intuition here. Let's go back to the bad example. I'll tell you that what's going on in that bad example is that this policy class is not closed under policy improvement. Okay. So what's the idea? Let's say that I start with a parameter that mostly has me moving left. Okay. So then when I do a policy iteration update, turns out that, hey, if I'm in the right state already, I want to stay right. But if I'm in the left state, I want to stay left. Okay? Now, if you could, the issue is that update is not in the one-dimensional policy class that kind of only lets you play the same thing at the two states. All right? And so you're getting stuck at this local minimum in that case. Okay. So in the remaining time, I'll just kind of give you a hint as to the other stuff we do in the paper. I think that's the punchline, is understanding these conditions under which policy gradient methods would succeed and when they would fail. Okay. Now, there's sort of three main extensions. One involves understanding the class of non-stationary policies. Okay, so for finite horizon problems, you usually use non-stationary policies, not these stationary ones. And I'll give you a hint that the curious thing that happens here is that we don't need policy closure. Okay. Instead, if the policy class contains the optimum in that case, then you're good. And I think the intuition for this is policy closure was a way of reducing a many-period problem to one-period problems. And there's kind of already something like a one-period problem in a finite horizon problem. It's the last period. Okay. And sort of some magic happens. All right. Now, the things that then are maybe a little deeper involve approximation with rich policy classes. Okay, so maybe the policy class is not closed under policy improvement, but I'm using a big neural network. It can solve most problems pretty accurately. Would I expect these things to work? Okay. Now, to kind of address this question, we can modify our theorem by saying that the policy class is no longer closed under policy improvement, but closed under an approximation to the policy improvement step. All right. So suppose that starting with a policy in my policy class, so some neural network policy, I can solve the policy iteration problem to width intolerance epsilon within my policy class. Okay. So I can almost solve one-period problems with my policies. All right. And then in the second step, I have the same condition. Okay. Then basically, you get a bound out that says that a stationary point of this objective should be near optimal up to a tolerance that scales with epsilon. Okay. And the numerator is some scary quantity that sort of depends on how well you explore the state space. Okay. And the last thing I'll sort of mention, so there I'll say I think that there's an interesting opportunity to kind of think through both rich policy classes that involve neural networks or so on, and the kinds of policy classes that we naturally use in OR problems, like Lagrangian relaxations or things like that, and ask, are these policy classes approximately closed? Okay, and if they are, I think that could give you a guarantee. All right. Now, the last thing that sort of we do in the paper, and I'll just kind of flash before we break up, is it's sort of natural to ask, okay, so any stationary point is a global optimum under certain conditions, but do you get to that stationary point at a reasonable rate? Okay. And sort of the punchline here is that, as before, you can just kind of peer at the policy iteration problem, the one-period problem. And say in the linear quadratic control case, that was a quadratic optimization problem. You can solve quadratic optimization problems rapidly using gradient descent. And so we're going to get as a corollary that policy gradient methods converge quickly. Okay. So what does that mean? All right, let's continue, just to give you one example of this. Let's continue to assume that the policy class is closed, like in linear quadratic control. And now let's assume the policy iteration problem is mu strongly convex, so like the quadratic optimization problem in linear quadratic control. Okay. Now, the special thing for our purposes about this function being strongly convex is it satisfies this kind of Polyak condition, which says that the distance of a policy pi theta from optimality is bounded by the norm of the gradient squared. There should be a square in that expression. Okay. So you're running gradient descent. You start making slow progress whenever the norm of the gradient gets small. Okay. But if you start making slow progress, you're almost optimal. All right. Now, it's going to turn out not that L, the loss function of policy gradient, is strongly convex. It's non-convex. But it does satisfy that Polyak condition. Okay. So again, the distance from optimality is bounded in terms of the norm of the squared gradient. So whenever policy gradient starts being slow, you're nearly optimal. All right. So two sort of comments here. One is, I should point out that for linear quadratic control specifically, this result is in that paper that motivated ours. Okay? But it's sort of shown directly. I think the win here is understanding that where that comes from is just nice structure in the one-period problem. Okay. I should also mention that this kind of Polyak condition is known to give convergence rates for smooth functions. Okay, so for Lipschitz functions that satisfy that condition, you get this kind of 1 over t convergence rate for free. All right. So
What is mu in that problem?
in the LQR problem, or
Yes, yes. How is it related to the input of the problem?
good. So mu.
What's the statement? There exists a mu? Or
There exists a mu. Now mu depends on the eigenvalues of these matrices. So I can't do it on the fly. It depends somehow on the eigenvalues of these matrices. Yeah. Okay. So I'll sort of pause here. Kind of the last thing is that if you actually did exact policy gradient for tabular problems, so in the finite state, finite action case, if you did exact policy gradient, you actually get geometric convergence. Right? Much like you would with policy iteration, again, kind of owing to the fact that there's such a tight connection between what's going on. Okay. Sort of pause here, and thank you, everyone.